There is a star so close to us that, on the scale of the galaxy, it is almost a neighbor. It belongs to the nearest stellar system beyond the Sun, only a little more than 4 light-years away. In the language of astronomy, that distance is small enough to sound intimate. In the language of engines, bodies, fuel, and time, it becomes almost impossible. Its name is Proxima Centauri, a small red star hidden in the southern constellation of Centaurus, too faint for the naked eye, too important to ignore. It gives no dramatic sign of itself in the night sky. It is smaller than the Sun, cooler than the Sun, and dimmer by an almost unimaginable margin. Yet in the long geography of space, it is the closest fire beyond our own. For centuries, humanity looked upward and imagined the stars as distant lights set into the dark. Then science slowly gave those lights size, heat, motion, chemistry, and age. The sky became a map. The map became a problem. And the problem became terrifyingly simple. The nearest star is close, and we still cannot go there. This is the strange humiliation of Proxima Centauri. It is the first step beyond the solar system, the obvious destination, the nearest possible answer to the oldest dream of interstellar travel. If humanity ever leaves the Sun behind and moves toward another star, this is the direction our imagination naturally turns. Yet between Earth and Proxima lies a distance so large that ordinary human language begins to fail. A spacecraft could cross oceans, continents, the distance to the Moon, the distance to Mars, and even the outer darkness beyond the planets, while Proxima would still remain ahead, almost unchanged in the sky. The closest star is a lesson in scale. It shows how small our triumphs become when measured against the real architecture of the cosmos. It is close enough to be studied, named, measured, modeled, and folded into human plans. It is distant enough to turn those plans into acts of patience almost beyond civilization. This is a journey toward Proxima Centauri, the closest star we may never reach. To understand Proxima Centauri, we must first understand the silence around it. When people imagine the nearest star, they often picture something bright, noble, almost solar, a second sun waiting beyond the edge of our system. Proxima is stranger than that. It is a red dwarf, small, cool, long-lived, and far less massive than the Sun. It burns with a low, persistent glow, more ember than blaze, and from Earth it remains invisible without a telescope. The closest star to the solar system hides from ordinary vision. This alone is a quiet correction to the human imagination. Proximity offers no guarantee of grandeur. The universe placed its nearest stellar neighbor in darkness. Proxima Centauri was identified in 1915 by the Scottish astronomer Robert Innes, working from South Africa. Its name comes from the Latin word for nearest, and the discovery carried a beautiful simplicity. Among the countless lights in the sky, this faint red point stood closer than all the others. It is possible to look toward that region of the sky and feel nothing unusual. The southern constellations still look like constellations. The black spaces between the stars still appear smooth and calm. The human eye cannot sense that in that direction, the entire story of interstellar travel becomes personal. 4¼ light-years sounds almost gentle because the phrase has been softened by repetition in documentaries, books, diagrams, and science fiction. But a light year is not a unit built for comfort. It is the distance light travels in 1 year, moving at about 300,000 kilometers per second. Light crosses the distance from the Moon to Earth in a little more than 1 second. It crosses the distance from the Sun to Earth in about 8 minutes. It crosses the width of the solar system on timescales that still fit within human thought. Then it keeps going for 1 year, and Proxima Centauri is more than 4 of those years away. Every image we receive of it is already old by the time it arrives. The light has been traveling since another season of human life, another political year, another generation of machines, another private collection of births, deaths, messages, journeys, and ordinary mornings. When we observe Proxima tonight, we see the star as it was over 4 years ago. The first step toward the nearest star is already a journey into the past. Proxima Centauri is often spoken of as if it were a lonely point at the edge of our reach, but it belongs to a larger stellar family. It is part of the Alpha Centauri system, the nearest known star system beyond the Sun. At its heart are Alpha Centauri A and Alpha Centauri B, two brighter stars locked in a long gravitational partnership. They are close enough to each other to form one of the most famous binary systems in the sky, and from Earth, their combined light appears as a brilliant southern star. Alpha Centauri A is broadly similar to the Sun, slightly larger and brighter. Alpha Centauri B is somewhat smaller and cooler, still recognizably solar in character. Together they form a pair that feels almost familiar compared with the dim red presence of Proxima. If humanity wanted a cinematic image of the neighboring system, these two stars would likely provide it. Twin suns moving through a slow orbital dance, shaping their surroundings with light and gravity. Proxima sits far away from this central pair, a distant companion moving through the outer reaches of the system. Its connection to Alpha Centauri A and B is gravitational rather than intimate. It belongs to the same stellar architecture, but at a wide separation that makes it feel like an outlying member of a celestial household. This structure gives the nearest star system a complexity that simple diagrams often erase. Our nearest neighbor is not a single star waiting in the dark. It is a triple system, with two sun-like stars and one faint red dwarf carrying the title of closest. This matters for the imagination of travel. A probe sent toward Proxima would enter a region where three stars define the sky. Proxima would be the local sun of its planets, while Alpha Centauri A and B could shine as unusually bright stars nearby. From some vantage points, they might appear as distant companion suns, a reminder that even the closest interstellar destination has its own depth, its own geography, its own hierarchy of light. The name Proxima can make the system sound simple. The reality is richer. The nearest stellar neighborhood is a small gravitational drama with bright stars, a hidden red dwarf, possible planets, uncertain orbits, and questions that reach from stellar formation to the future of exploration. Before we even speak of crossing the distance, the destination itself asks us to think in 3 dimensions. Before we can imagine crossing to Proxima Centauri, we must understand what it means to leave home. The solar system is often represented as a neat sequence of planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The diagram fits on a page, and the planets appear close enough for the mind to hold them together. Those diagrams are acts of mercy, because the real solar system is mostly empty distance. Earth circles the Sun at about 1 astronomical unit. Mars, at its closest, still sits tens of millions of kilometers away. Jupiter is a kingdom of its own, so distant that sunlight arrives there weaker, colder, and more patient. Saturn takes almost 30 Earth years to complete one orbit. Neptune moves so slowly that one Neptunian year lasts about 165 Earth years. Beyond Neptune lies a field of icy bodies, and beyond that, the Sun's influence fades into the deep heliosphere where the solar wind meets the interstellar medium. The Voyager spacecraft have crossed into this region, carrying instruments, old radio signals, and small human messages into the surrounding dark. Voyager 1 is among the fastest and farthest objects humanity has ever sent outward. It has been traveling since 1977. It passed the outer planets, crossed the heliopause, and entered interstellar space. Compared with the distance to Proxima Centauri, that extraordinary journey has barely begun. This is the first psychological wall. We often treat interstellar space as the next frontier after the planets, as if the outer solar system were a coast and the stars were islands beyond it. The true scale is harsher. The distance between planets is enormous. The distance between stars belongs to a different order of reality. If the Sun were a small sphere in one city, the nearest star would be across a continent of darkness. Human exploration has always depended on the transformation of distance into route. The ocean became navigable because ships could survive the crossing. Continents became connected because roads, rails, engines, and maps turned hardship into infrastructure. The moon became reachable because physics, money, politics, and engineering converged for a brief and extraordinary moment. Proxima Centauri asks for something larger, whether distance itself can be broken. A chemical rocket, like those that carried humans to the moon, cannot make the journey in any meaningful human timescale. Even our fastest probes would take tens of thousands of years to arrive if aimed toward the nearest stars. The human body is fragile, machines decay, civilizations change their languages, their fears, their borders, and their gods. A mission to Proxima would have to outlast almost everything we normally call a mission. It would have to become a message to the future. Proxima Centauri itself is modest by cosmic standards. It has only a fraction of the Sun's mass. Its diameter is far smaller. Its light is faint, mostly red and infrared, gentle in total output compared with the brilliant white-yellow presence that rules our sky. A world orbiting far from Proxima would freeze. To receive enough warmth, the planet must orbit much closer than Earth orbits the Sun. Around a red dwarf, the habitable zone is drawn inward, close to the star, where years become short and skies become strange. Proxima is also active. It is a flare star, capable of sudden eruptions of radiation. Its magnetic life can be violent, and for any planet nearby, habitability becomes a question written in storms. A red dwarf can live for an extraordinary length of time, much longer than the Sun. The universe may one day become an age of red dwarfs, after larger stars have burned out and faded. These small stars spend their fuel slowly. They belong to deep time. Proxima, the closest star, therefore offers a preview of the far future. It is a smaller fire, stubborn and ancient in its promise. If one could approach it from interstellar space, it would grow slowly from a faint red point into a dark ember. There would be no sudden sunrise like the one Earth knows. There would be a deep red light, an unfamiliar spectrum, and a sky shaped by proximity and danger. There is a temptation to romanticize the nearest star, to treat it as the next campfire, the next harbor, the next destination after the solar system. Proxima resists that simplicity. It is governed by its own physics, placing its planets under conditions that Earth never had to endure. This matters because humanity dreams of finding something there. We are drawn to the closest star because it is reachable in theory and mysterious in practice. A red dwarf can appear calm from a distance, but Proxima Centauri is magnetically restless. It can produce stellar flares, sudden releases of energy that send radiation outward through space. For a planet orbiting close enough to receive warmth, those flares are not a distant spectacle. They are part of the weather of existence. Around a small star, closeness is a necessity, and that necessity places any planet inside the reach of the star's violence. Imagine a rocky world circling Proxima in a year lasting only days. Above its surface, the star hangs large in the sky. For long stretches, the light may seem stable, low, red, and quiet. Then the star changes. Its magnetic fields reconnect, its atmosphere erupts, and radiation sweeps outward. Ultraviolet light, charged particles, and bursts of energy reach the planet. If the world has an atmosphere, that atmosphere becomes the first line of defense. If the atmosphere is thin, damaged, or absent, the surface becomes far more exposed. This is one of the central problems of life around red dwarfs. These stars are common across the galaxy, which makes them tempting homes for habitable planets. Their small size makes Earth-sized worlds easier to detect. Their long lives provide enormous time for chemistry and evolution. Yet their activity can punish the planets that orbit close enough to be warm. A world may sit in the mathematical habitable zone and still face conditions that strip air, erode water, and sterilize exposed ground. The question is therefore subtle. A planet around Proxima does not need a gentle star in order to matter. It needs protection, resilience, and the right history. A dense atmosphere might redistribute heat and absorb radiation. A magnetic field might deflect charged particles. Oceans, rock, chemistry, and underground environments might shelter fragile processes from the sky. Life on Earth has found refuge in darkness, pressure, ice, heat, and poison. The question is whether a world under a flaring red sun can keep enough stability for life to begin and endure. For a video about Proxima, this danger is essential. It prevents the story from becoming a simple fantasy of a nearby second Earth. The closest known exoplanet lives in a system where warmth and hazard come from the same source. Proxima gives with one hand and threatens with the other. Any world around it must negotiate with a star that can last for trillions of years while still erupting with sudden violence. Proxima b became famous because it was close, roughly Earth-sized, and located in a zone where liquid water might exist under the right conditions. Yet its discovery also reveals something profound about modern astronomy. We found this planet without seeing it directly. No telescope produced a clean image of a blue or red globe. No instrument resolved continents, clouds, oceans, ice, or surface. The planet announced itself through the motion of its star. Astronomers detected Proxima b using the radial velocity method. A planet and a star orbit their common center of mass. The star is far more massive, so its motion is tiny, but the movement exists. As the star wobbles slightly toward and away from us, its light shifts by a small amount. The change is delicate, almost absurdly small, hidden inside noise, stellar activity, and instrumental limits. With enough precision, patterns begin to emerge. This is one of the great achievements of exoplanet science. We have learned to hear planets through the trembling of stars. The gravitational pull of an unseen world becomes a rhythm in the data. A line in a spectrum moves, returns, repeats, and slowly the invisible takes shape. In the case of Proxima b, the signal indicated a planet with a mass close to Earth's, orbiting every 11.2 days, extremely close to a faint red star. There is a poetry in that method, but it is a disciplined poetry. A planet is inferred through mathematics, repeated observation, statistical confidence, and the careful separation of stellar noise from planetary motion. The public imagination often jumps straight to alien landscapes. The actual discovery began with instruments, spectra, uncertainty, and the patient art of detecting a small gravitational whisper. This makes Proxima b feel even more distant. It is the nearest known exoplanet, yet it has never been seen as a place. We know it through effects rather than appearance. We can measure its orbit more easily than we can picture its sky. We can estimate its minimum mass more confidently than we can describe its surface. It exists at the boundary between fact and image, real in data, open in imagination. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri. Its name is Proxima Centauri b. The discovery felt almost too perfectly timed for the human imagination. The nearest star had a planet. That planet was roughly Earth-sized. It orbited within the region where temperatures might allow liquid water under the right conditions. The closest star system became more than a target. It became a question. Could there be a world there? Proxima b orbits its star in only about 11.2 Earth days. Its year is shorter than 2 weeks. It moves at a distance of roughly 5/100ths of an astronomical unit from Proxima, far closer to its star than Mercury is to the Sun. Because Proxima is so dim, that close orbit may place the planet in the habitable zone. Habitability is one of the most powerful words in astronomy and one of the easiest to misunderstand. It means that, under a narrow set of assumptions, a planet receives enough stellar energy to allow liquid water at the surface. That possibility carries the whole mystery. Proxima b may be rocky. It may be tidally locked, with one side always facing the star and the other turned permanently toward space. If so, one hemisphere could live beneath a fixed red sun while the other remains in endless night. Between those two extremes, a ring of twilight might exist, a borderland where temperatures become less severe, or the planet may have an atmosphere capable of redistributing heat. Or it may have lost that atmosphere long ago under the pressure of stellar radiation. It may be dry, frozen, scorched, geologically quiet, chemically active, or stranger than any of those categories. We do not know, and that ignorance is part of the power of Proxima b. The planet is close enough to become a real scientific target and far enough to remain almost entirely unreachable by direct experience. We can detect its gravitational whisper in the motion of its star. We can infer its orbit. We can estimate its minimum mass. We can simulate climates that may or may not resemble anything real. No telescope has shown us its surface. No spacecraft has passed above its clouds. No lander has touched its soil. The nearest known exoplanet is still a locked room. That locked room may contain a dead rock, a wounded atmosphere, a frozen hemisphere, a red-lit desert, a buried ocean, or a chemistry we have not yet imagined. The fact that it exists at all around the nearest star is already enough to change the emotional map of the sky. The discovery of Proxima b produced a wave of hope because humans are trained by story to search for mirrors. A planet near the closest star immediately becomes Earth-like in the public imagination. We give it oceans before we have seen water. We give it skies before we know whether it has air. We give it life because life is the question beneath almost every space story. Science advances by resisting the comfort of premature certainty. Proxima b lives close to a red dwarf. Red dwarfs are common, perhaps the most common stars in the galaxy. If their planets can host life, then habitable worlds may be widespread. If their activity strips atmospheres and sterilizes surfaces, then a large fraction of the galaxy's apparent promise may be harsher than it looks. This is why Proxima matters far beyond its distance. It is a laboratory for one of the great questions of astrobiology. Can life endure around small active stars? Can atmospheres survive the flares? Can oceans persist under red light? Can biology adapt to long-term radiation stress, tidal locking, and extreme stellar behavior? On Earth, life has endured much. It has survived ice ages, impacts, volcanic winters, deep-sea darkness, radiation, pressure, starvation, and chemical extremes. Earth teaches us that life can be persistent once it begins. Proxima b asks whether life can begin and survive under a different sky from the start. If the planet has an atmosphere, that atmosphere may separate a dead stone from a world. If it has a magnetic field, that field may help shield it. If it formed with enough water or gained water later, some of that water might remain. If its night side is cold enough, volatiles could freeze there. If circulation is strong enough, heat might move around the globe. Every sentence about Proxima b becomes a chain of conditions. The planet is real while the world remains hypothetical. This is where the poetry of space must accept the discipline of uncertainty. Proxima b is among the most emotionally powerful exoplanets ever found because it sits so close to us. It is also frustrating because closeness does not give us the view we want. We know enough to imagine. We know too little to conclude. Proxima b receives most of the attention, but the system may contain more than one planet. Proxima d has been reported as a small inner candidate, orbiting extremely close to the star in only about 5 days. Another candidate, often called Proxima c, has been discussed as a possible more distant world, though its status has been debated. The result is a system that may be more layered than the simple phrase "closest planet" suggests. This hidden architecture matters because planetary systems are histories frozen into motion. The distance of a planet from its star, the shape of its orbit, the presence of neighbors, and the amount of material left from formation all tell a story. Around a small red dwarf, those stories can be compressed into tight spaces. The inner regions are close, fast, and exposed. A planet can complete a year in days. The habitable zone lies close to the furnace. Gravitational interactions unfold on scales far smaller than those of our own solar system. If Proxima d is real as described, it circles inside the habitable zone, closer to Proxima than Proxima b. It would receive far more stellar energy, making surface conditions severe by Earth-like standards. Yet its existence would show that the nearest star may host a compact system of small worlds. That alone matters. It suggests that planet formation around Proxima produced more than a single object, and that the nearest stellar neighbor may contain a miniature planetary architecture still coming into focus. Proxima c, if confirmed or clarified by future observation, would add another layer. A possible outer world, perhaps colder, slower, and more distant. Even uncertainty has value here. It shows the difficulty of studying small planets around active stars. Signals can be faint. Stellar noise can imitate or obscure planetary rhythms. Instruments improve, interpretations change, and the system slowly sharpens through years of observation. For the story of Proxima, this gives us a broader frame. We are not simply asking whether one planet could host life. We are asking what kind of planetary system exists around the nearest star. Is it sparse or crowded? Stable or dynamically complex? Dry, irradiated and barren, or rich with worlds shaped by red light? The closest system beyond the Sun is still being mapped, and every new signal changes the outline. Proxima Centauri is the nearest star, but it is also the first member of a larger neighborhood. Beyond the Sun lies a local region filled mostly with faint stars, red dwarfs, dim companions, brown dwarfs, and a few brighter points. The cosmic neighborhood is less like a gallery of solar twins than a dark suburb of small, persistent fires. Proxima is first because it is closest, but it belongs to a population that dominates the galaxy by number. After Alpha Centauri and Proxima, the stellar map opens toward other nearby names: Barnard's Star, Wolf 359, Lalande 21185, Sirius, Epsilon Eridani, Luyten's Star, Ross 128, and many more. Some are too faint to see without instruments. Some have become famous because of suspected or confirmed planets. Some are bright because they are intrinsically luminous, while others remain obscure despite their proximity. The local sky, once examined closely, becomes a list of personalities rather than a scatter of lights. Barnard's Star, for example, is one of the nearest individual stars and one of the fastest moving across Earth's sky. It is another red dwarf, another reminder that the galaxy's common stars are modest. Sirius, by contrast, shines brilliantly from Earth and carries a white dwarf companion, a dead stellar core beside a blazing primary. The neighborhood around the Sun is therefore varied, but its most numerous inhabitants are small, faint, and long-lived. This context changes the meaning of Proxima. It is not simply a target, it is the threshold of a local map. If humanity ever learns to send probes to nearby stars, the first journey may lead to Proxima, but the second and third would already have names. Interstellar exploration would begin as a slow expansion through the solar neighborhood, from one faint star to another, from one set of planets to another, building a real geography beyond the Sun. The first step matters because it defines the scale of every step after it. If Proxima is too far, then all stars are too far. If Proxima can be reached, even by a tiny probe, then the galaxy changes category in the human mind. It remains immense, but the nearest part becomes a frontier with coordinates, targets, travel times, risks, and priorities. The local stellar neighborhood becomes the first true territory of interstellar thought. Suppose we decided to go. Suppose humanity chose Proxima Centauri as its first interstellar destination. Suppose the political will existed, the money existed, and generations agreed that this was worth doing. The first problem would be speed. The fastest spacecraft humans have built move at impressive speeds by earthly standards. They can leave Earth, cross planetary orbits, and escape the Sun. Compared with light, they crawl. At tens of kilometers per second, a probe aimed at Proxima would need many tens of thousands of years. By the time it arrived, every nation that launched it might be gone. Every language used in its command sequences might be ancient. Every person involved in its construction would belong to archaeology. This is travel beyond the emotional scale of civilization. To reach Proxima in a humanly meaningful time frame, we need a substantial fraction of light speed, 1/10, 1/5, perhaps more. These numbers sound clean in theory, almost elegant on paper. In engineering, they become brutal. A spacecraft moving at 20% the speed of light would cross interstellar space fast enough to reach Proxima in a few decades. But accelerating anything to that speed demands enormous energy. Protecting it from dust becomes a problem of survival. Even a tiny particle at such velocity can strike with destructive force. The empty space between stars is not perfectly empty. It contains atoms, dust grains, magnetic fields, cosmic rays. At ordinary speeds, these are background conditions. At relativistic speeds, they become hazards. Then comes the problem of slowing down. A probe that races toward another star must either fly past in hours or carry some method of deceleration. Speed gives arrival. Deceleration gives encounter. Without deceleration, Proxima becomes a blur after decades or centuries of flight. There are ideas: laser-driven sails, fusion propulsion, antimatter concepts, nuclear pulse designs, generation ships, autonomous probes small enough to accelerate quickly, and swarms of microcraft instead of one grand vessel. Each idea opens a door and reveals another wall. The difficulty of Proxima is useful because it forces propulsion to leave fantasy and become calculation. Energy, mass, shielding, communication, guidance, heat, and endurance all become part of the same unforgiving equation. Even success would be strange. A message from Proxima would not arrive instantly. It would take more than 4 years to come back. Every photograph would be a delayed resurrection. Every measurement would say, "This is what the closest star system was 4 years before you received it." Interstellar travel stretches conversation until it becomes memory. Among the serious ideas for reaching the nearest stars, the most striking is the laser sail. A conventional spacecraft carries fuel, and fuel adds mass. More mass requires more fuel, and the logic quickly becomes punishing. A laser sail tries to shift part of the burden away from the spacecraft. The vehicle becomes tiny, perhaps gram scale, attached to a thin reflective sail. A powerful beam of light pushes it from behind, accelerating it without requiring a large onboard engine. This is the basic vision behind Breakthrough Starshot, ultra-light nanocraft driven by intense laser beams toward the Alpha Centauri system. The concept sounds fragile because it is fragile. A probe small enough to ride such a beam would carry miniature cameras, sensors, computation, communication hardware, and power within an almost impossibly small mass budget. Its sail would need to survive enormous acceleration while reflecting the beam without vaporizing. The laser array would need to remain coherent, accurate, and powerful enough to push the craft toward a significant fraction of light speed. If such a system worked, the journey time could fall from tens of thousands of years to decades. That is the transformative promise. A probe launched by one generation might reach the nearest star while some of that generation is still alive, or while their children can remember the day it left. Interstellar travel would no longer belong only to deep time. It would enter human history, even if the mission itself remained small, risky, and incomplete. The challenges are severe. The beam must stay focused across vast distances during acceleration. The sail must maintain stability. The craft must survive collisions with interstellar dust at tremendous velocity. It must navigate without repair, endure cold and radiation, gather data during a rapid encounter, and transmit information back across more than 4 light years. The return signal would be weak, delayed, and precious. A handful of images could represent one of the most technically difficult messages ever received. The beauty of the laser sail is that it changes the shape of the problem. It gives humanity a possible first step that avoids the impossible scale of crude interstellar travel. The tragedy is that the first step would be almost ghost-like, a tiny machine crossing the darkness too quickly to stop, carrying no human body, no flag, no voice, only instruments and memory. It would be the fastest machine we could ever build, aimed at the closest star with only a few hours to turn decades of travel into knowledge. Imagine that such a probe survives. It leaves Earth, accelerates under a beam of light, crosses the outer solar system, and enters the long emptiness between stars. Years pass, decades pass. The probe becomes a point of intention moving through cold darkness. It cannot repair itself. It cannot ask for help. It carries its instructions inside circuits that must remain alive through silence, radiation, and time. Then the Proxima system grows ahead. After a journey that lasted a large fraction of a human life, the encounter itself may last only hours. At a significant fraction of light speed, there is little time for correction, hesitation, or ceremony. The spacecraft races through the system, perhaps past Proxima b, perhaps through the wider environment of the red star, gathering whatever it can: images, radiation data, particle counts, magnetic measurements, evidence of atmosphere if the geometry allows it. This is one of the strangest asymmetries in exploration. Decades of preparation, decades of flight, and then a brief passage through the destination. The probe cannot enter orbit unless it carries a solution for slowing down, and slowing down is among the hardest problems of all. A flyby mission is therefore an act of extreme compression. A lifetime of travel becomes a narrow window of observation. During that window, everything matters. Where is the planet? What face does it show? Is there cloud cover? Is there a sign of atmospheric scattering, aurora, dust, ice, or reflected red light? Does the star erupt during the encounter? Can the craft point its instruments accurately while moving at a terrifying speed? Can it store the data? Can it turn its signal back toward a tiny blue planet orbiting a distant yellow star? Then the probe is gone, continuing into deeper interstellar space. It may never stop. It may become a relic traveling forever beyond the nearest system, carrying the memory of a world it saw only briefly. Behind it, after more than 4 years of light time, Earth waits. If the signal arrives, humanity receives a few fragments from the closest star. Perhaps a blurred image, perhaps a curve of light, perhaps measurements that take years to interpret. A few hours near Proxima could feed science for generations. A crude journey to Proxima Centauri belongs to a different category of dream. A small probe can be sacrificed to speed. A human mission must carry life support, shielding, food, water, governance, medicine, repair systems, social structures, psychological stability, and some way to preserve meaning across time. If the journey lasts centuries, the ship becomes a world. The first generation leaves Earth. The second inherits motion. The third may know Earth only as archive, image, myth, instruction, and grief. Children would be born inside a machine aimed at a star they did not choose. Their descendants might arrive at Proxima with no living memory of the planet that launched them. This idea has appeared often in science fiction because it exposes the moral difficulty of interstellar ambition. A generation ship is a society designed around a destination that most of its inhabitants will never see. It would need education, law, culture, medicine, reproduction, maintenance, agriculture, conflict resolution, and rituals strong enough to bind people to a goal older than their own lives. Who has the right to impose a journey on the unborn? Who governs a vessel that cannot turn back in any practical sense? What happens if the destination disappoints? What happens if Earth changes its mind centuries after launch? What happens if the ship itself becomes the only home its people can understand? Proxima Centauri becomes, in this frame, less a place than a test of continuity. Can human purpose survive beyond a single lifetime? Can a project remain meaningful after its founders are dust? Can a civilization act on behalf of descendants distant enough to be strangers? We already do this in smaller ways. We build cathedrals that outlast their architects. We plant forests we will not sit beneath. We store warnings about nuclear waste for people who may not speak our language. We send spacecraft outward with records of our species attached to them. A human mission to Proxima would enlarge that habit until it became the central fact of existence. The ship would carry passengers, memory, law, language, ritual, conflict, repair, education, and inheritance. It would carry a compressed civilization. Outside the walls, for year after year, decade after decade, there would be nothing but interstellar night. The destination would be a star, but the true experiment would be the survival of meaning between stars. Imagine arriving. After the long crossing, the star ahead grows brighter. It never becomes a sun in the familiar sense. It glows red, small, intense, close to its worlds. The Alpha Centauri pair may shine elsewhere in the sky as brilliant companions, distant suns within the same gravitational family. Proxima b, if visible, would move close to its star. If tidally locked, one hemisphere would face endless day, though the word day would lose much of its earthly meaning. The star would hang in place, unmoving, a red disk suspended over the same landscapes for all time. On the day side, light may be dimmer in visible wavelengths than sunlight on Earth, yet the star would dominate the climate. Flares could suddenly change the radiation environment. Skies, if skies exist, might glow in unfamiliar colors. Clouds could gather near the substellar point. Winds could move heat toward the night side. The night side might be frozen beneath a permanent sky. If an atmosphere is present, weather may connect the two hemispheres. If the atmosphere is thin or absent, the planet could be a world of extremes. Red-lit heat on one side, black cold on the other, twilight between them. The twilight zone is the place the imagination returns to, a ring around the planet where the star sits low forever, where ice and rock and wind may meet under a fixed horizon. If water exists, perhaps it gathers there. If life exists, perhaps it learns the geometry of eternal sunset. This is speculation, but speculation grounded in physics has a special texture. It sketches the range of possible worlds without claiming the world itself. Proxima b could be barren. It could be beautiful in a way that no human eye has seen. It could be the nearest example of a living planet beyond Earth. It could be a warning that habitability is a fragile word. For now, it remains unresolved, and that unresolved quality is part of its hold on us. A known planet, around the nearest star, close enough to name, too far to touch. A place suspended between measurement and imagination. A world we can calculate, model, and dream toward while still remaining outside the reach of human experience. A future telescope may never show Proxima b as a detailed globe, yet even a small amount of light could carry enormous information. Astronomy often begins with almost nothing. A point, a spectrum, a tiny dimming, a shift in color, a pattern repeated over time. From these fragments, scientists reconstruct temperatures, orbits, masses, atmospheres, and sometimes chemistry. A single, unresolved point can become a world through patient measurement. If future instruments separate the planet's light from the glare of Proxima, they may search for signs of an atmosphere. A spectrum could reveal molecules if enough photons are gathered. Water vapor, carbon dioxide, methane, oxygen, ozone, or other compounds would each raise different questions. No single molecule would prove life. Context would matter. The star, the planet's history, the atmosphere's stability, geological activity, and the possibility of non-biological chemistry. This is where Proxima becomes a powerful scientific target. Its closeness means that, compared with more distant systems, its planets are more accessible to detailed study. The star is small, which can help certain detection techniques. The planet's orbit is short, allowing repeated observations. Its difficulties are real: stellar activity, flares, noise, and the challenge of separating planetary signals from the behavior of the star. Yet every difficulty also teaches astronomers how to study red dwarf systems more broadly. The search for life may advance slowly. It may begin with atmospheric survival rather than biology. Does Proxima b have air? Does that air change over time? Is there evidence of clouds? Does the planet reflect light in a way consistent with surface ice, ocean rock, or haze? Are there seasonal or orbital variations? Can stellar flares be separated from planetary signals? These questions sound technical, but each one moves the locked room closer to becoming a place. One day, the first great discovery from Proxima may be modest. An atmosphere exists, or it does not. The planet is dry, or it may not be. The star is more damaging than expected, or less. Such findings would still matter. They would tell us whether the nearest potentially temperate world is a graveyard, a survivor, or a mystery still open. Sometimes the most important image is not an image at all, but a line of light that refuses to be simple. There is something almost cruel about Proxima Centauri. The universe placed the nearest star close enough for us to measure, study, name, model, and dream about. Close enough to make interstellar travel feel like a technical challenge rather than a fantasy. Then it made that closeness enormous. 4.25 light years, a small number written beside an impossible distance. This is why Proxima has philosophical weight. It marks the boundary between astronomy and pilgrimage. We can know it as a star. We can calculate its properties. We can infer its planets. We can point instruments toward it and collect photons that began their journey years earlier. But to go there physically, with mass, machinery, and intention, is to confront the deeper structure of the universe. The solar system has trained us to believe that distance can be conquered by effort. The stars may require a different kind of humility. A mission to Proxima would differ radically from Apollo. Apollo moved within the immediate neighborhood of Earth, under constant urgency, within the pulse of a single political age. Proxima asks for patience measured in decades at best, centuries more realistically for large craft, and perhaps millennia under technologies we already possess. The moon was a destination. Proxima is a horizon. A horizon can guide movement even while it remains distant. It organizes ambition. It gives direction to research, engineering, astronomy, propulsion, artificial intelligence, materials science, long-duration life support, and planetary science. Even if we never reach it, Proxima changes us because it defines the first serious question of interstellar civilization. What would it take to leave the sun behind? The practical mind may ask why any of this matters. If Proxima is unreachable for now, if Proxima b may be sterile, if the journey is too long, too expensive, and too dangerous, why care? Because proximity has meaning. The nearest star is the first measurement of our confinement. It tells us the size of the room in which humanity has awakened. We live on a planet around one star, inside one system, in one ordinary region of one galaxy. For most of history, that system was all we could touch. Now we can see beyond it with precision, but vision and travel remain separated by a gulf. Proxima Centauri is the nearest object that forces us to admit that gap. It is also a reminder that discovery does not require arrival. We may learn more about Proxima b with future telescopes. We may study its atmosphere, if it has one. We may detect signs of chemistry that narrow the possibilities. We may find additional planets. We may observe the flares of the star, map its activity, and understand whether its environment is hostile to life or simply different from ours. The first truths may come by light alone. That is how astronomy has always worked. The universe sends messengers, photons, particles, gravitational waves. We catch them with instruments and build worlds in the mind. Long before any ship can cross the distance, knowledge can travel. And knowledge changes the emotional map. If Proxima b shows signs of an atmosphere, the nearest star becomes more compelling. If it appears stripped and dead, the lesson is still profound. If another planet in the system is confirmed, the architecture grows richer. If future observations reveal something unexpected, the closest star may become the center of a new chapter in planetary science. We do not need certainty for Proxima to matter. Its importance comes from its position. It is first beyond the sun. Every cosmic subject eventually returns to scale. A human life is brief. A star can burn for billions or trillions of years. A planet can circle through epochs longer than civilization. A beam of light can cross human history in an instant or spend years traveling between neighboring stars. Proxima Centauri sits at the edge of what the human mind can hold emotionally. 4 years for light, tens of thousands of years for current spacecraft, decades for speculative microprobes, centuries or more for human-scale vessels. These numbers create a ladder, and each rung asks for a different version of humanity. The first version is the one we already are, observers who look, measure, model, publish, correct, and refine. The second is the builder of probes, willing to send small machines into darkness and wait half a lifetime for a reply. The third is the builder of civilizations that can plan beyond individual lives. The fourth is something we may never become. There is no shame in that. The universe does not owe every destination to every species. Some places may exist as limits. Some distances may remain clean and immense, untouched by engines, holding their silence across deep time. But limits are rarely useless. They shape imagination. They discipline ambition. They reveal the size of the task. Proxima Centauri is the nearest stellar limit. When we name it, we name the beginning of the unreachable. We also name the first place where humanity must decide whether exploration is only a matter of going, or also a matter of understanding the scale of what cannot yet be crossed. Picture one day, a small probe leaving the solar system at a speed no spacecraft has ever achieved. It is light, perhaps no larger than a human hand, perhaps carrying a camera, sensors, a transmitter, and a memory of Earth compressed into metal and code. It is pushed by light, or by some technology still unfinished in laboratories and equations. It leaves the planets behind. It passes the outer dark. It enters the long corridor between stars. There are no planets to pass, no moons, no clouds, no continents, only time, radiation, dust, silence, and the faint mathematical pull of distant suns. Years pass on Earth. The people who watched the launch grow older. The children who learned its name become adults. The mission becomes less news than background, less spectacle than waiting. It belongs to calendars, institutions, archives, and a shrinking group of people who still remember the emotion of departure. Then, decades later, it reaches the Proxima system. Perhaps it survives. Perhaps it turns its instruments toward the red star. Perhaps it catches a glimpse of Proxima b, a crescent or a point, a world resolved only slightly from the dark. Perhaps it measures plasma, dust, radiation, magnetic fields. Perhaps it sees nothing dramatic and sends back data that looks at first almost ordinary. Then the signal travels home. For more than 4 years, the message crosses the same emptiness the probe crossed, a whisper moving at the fastest speed the universe allows. At last, Earth receives it. A few numbers, a few images, a confirmation that something made by human hands reached the nearest star. If that day comes, it will be one of the quietest revolutions in history. No human being will stand there. No flag will move in alien wind, no voice will speak from the surface, and yet the boundary of our species will have changed. For the first time, the solar system will no longer contain the full extent of human artifacts. Somewhere beyond the sun, a machine from Earth will have entered the light of another star. There is a final possibility we must allow. We may never reach Proxima Centauri. Our telescopes may improve. Our simulations may become exquisite. Our maps may grow more detailed. Our understanding of red dwarfs and exoplanets may deepen for centuries. But no vessel from Earth may ever enter that system. No human may ever see its red star with their own eyes. No machine may survive the crossing. This possibility does not make Proxima less important. Some destinations matter because they are reached. Others matter because they reveal what reaching truly means. Proxima Centauri is close enough to tempt us and distant enough to humble us. It is a star at the edge of our practical imagination. It tells us that the galaxy is a structure of real distances, real hazards, and real timescales. It also reminds us that the dream of space is not always about arrival. Sometimes it is about learning the shape of longing, Sometimes it is about discovering that the first step beyond home is already vast beyond measure. We live beside a star. Around us, planets move through sunlight. Beyond Neptune, our machines drift outward, still carrying the faint warmth of human intention. Beyond them lies the deep interstellar medium. Beyond that, after years of light, a small red dwarf burns in silence. Proxima Centauri, the nearest star, the first neighbor, the first wall, a red ember at the edge of human reach. And perhaps for a long time, the closest place in the universe that remains beyond us.